Hey, and welcome to my YouTube channel. Today we're going to talk about chemistry, specifically intermolecular forces. So when dealing with STEM, particularly chemistry, biology, and physics, I think it's really important to first define terms that we're going to be using. And today, since we're talking about intermolecular forces, let's define that. So without looking at Wikipedia or Googling the definition of intermolecular forces, the best way I would describe it is the attraction between two or more different molecules. So this is in direct contrast to intramolecular forces, which would be RA as opposed to ER, which are forces that attract atoms within a molecule. So if you saw my last video, let me pull up let me draw here. If you saw my last video, we were talking a little bit about hydrogen bonding. And I remember we drew a water molecule here, and I proposed the question, is this a hydrogen bond? And like I said in the video, some people may confuse this to be a hydrogen bond because it has hydrogen, it has oxygen, and you might think, well, if this is water, it has to be a hydrogen bond. But that's not the case because the bonds here between the hydrogens and the oxygen are actually intramolecular forces because yes, there are two different bonds, but they're all within one molecule. That being said, if there were two molecules, let's say there was water over here, and we had an attraction between, excuse me, my bad. And we had an attraction between an oxygen and a hydrogen over here, or this oxygen and this hydrogen, that would be a type of intermolecular force because we can label one, two different molecules that are interacting with each other. So keep in mind here, we're talking about multiple molecules, more than one. So let me go ahead and clear out these things and bear with me because this can take forever and I'm not sure. Looks like there's an eraser up there, but I'm pretty stubborn. So below intermolecular forces, I've given you all some of the most common ones that you'll talk about in maybe your AP chemistry course or chemistry in college. So we have hydrogen bonding, dipole dipole, dipole-induced dipole, ion-induced dipole, and then dispersion forces. And these are all types of intermolecular forces. So beginning with hydrogen bonding, essentially it's what I drew in the bottom right corner, right? It is an electronegative atom attached to a hydrogen that is also attracted to another molecule that is electronegative. For example, two water molecules, right? The interaction between the delta negative of the water or the full negative of the oxygen attracts the slightly positive hydrogen. And that sort of gives you an intermolecular force that you might see in your glass of water, or perhaps another molecule that is attached, like a hydrogen attached to an oxygen or a nitrogen or a fluorine. So that's hydrogen bonding. And in terms of intermolecular forces, it's pretty strong, right? Obviously, it's not as strong as covalent or ionic, but those are all intramolecular forces for the most part we're talking about. So dipole dipole, I think I will try to illustrate here the best I can. Dipole dipole is essentially when you have attraction between the positive and negative sides of two molecules or more molecules. So let's draw molecule one, and we'll do like a negative, and then a positive. And then we'll draw molecule two, right? And this is just for the sake of simplicity. Obviously, this is not an extremely accurate drawing. So you probably recall from maybe Gen Chem, or maybe you forgot, or maybe you're just learning this for the first time, that there is a sort of polarity within a lot of molecules, right? There may be a covalent bond, but it might not necessarily be sharing as much as like a hydrocarbon, where it's equal. So if you happen to have a dipole moment, that is that there's, the charges don't cancel out to the point where you have a clear positive and a clear negative, then you're going to have a bit of a dipole moment. And it is the attraction between the negative side of one molecule and the positive side of another molecule that gives you an intermolecular force here. So that is a dipole-dipole. Two molecules that already have dipoles that would have a dipole moment of their own are attracted to each other. With their separate molecules, this is an intermolecular force. Moving on to dipole-induced dipole. This time we're going to talk a little bit more about polarity. So let's say you have a molecule that has a dipole moment, right? It has a net dipole. You can do your calculations, whatever. You visually look at it, you're like, okay, well, this is clearly polar. It has some polarity to it. But let's say you have this, and then you have something that's nonpolar. So maybe a hydrocarbon or something like that. But for our purposes, we'll just call it a blue circle. So if this blue circle is neutral, the intermolecular force part of this comes from, let's say this has positives and negatives, but for the most part, there's no dipole moment. This positive charge of this other molecule is going to sort of pull at whatever negative charge resides inside this molecule, if that makes sense. This is sort of acting like a magnet where it's pulling on the negative charge, and vice versa. If this was facing the opposite direction, the negative side of this might attract the whatever positive charge is within the nonpolar molecule. But for example, if we're just talking about the positive and the negative, this would sort of force this nonpolar molecule to have a net dipole. Now, normally it doesn't have a dipole at all, but it's sort of like having, let's say, a balloon that's a complete circle, and then you're pulling a piece of that balloon, changing its shape, and then making it so that it's not completely even like it was before. So that's dipole-induced dipole. Ion-induced dipole is very similar. So we'll erase this. Give me a second. So we will use a green circle. And let's say this is a hydrocarbon, for example, or something like that. That's nonpolar, okay? And when we say nonpolar, we mean that it has really no charge. It doesn't have a dipole moment. And we can also talk about the geometry here, but that's a whole nother video. So let's say this is nonpolar, right? And then we have an atom like sodium hanging out over here. We know that sodium often has a positive charge. So the positive charge, just like in the dipole, induced dipole, is going to interact with whatever negative charge is in here, right? So, there's negatives in here, there's positives in here, but pretty much they just cancel out. So the positive is going to sort of attract the negative, and it's going to pull the balloon or the molecule to force a dipole. And this is an intermolecular force. It is not a covalent bond, just like hydrogen bonding or dipole-dipole or dipole-induced dipole. It's between two or more molecules. So similar concept for ion-induced dipole. So lastly, to wrap this up, we're going to talk a little bit about dispersion forces. The best way I can explain dispersion forces is by giving you sort of an analogy that my professor gave me when I was in Gen Chem 2, which was like, okay, imagine if you have a gym class of students, right? And they're all running. Maybe you all want to have a little drawing here just for fun, And there's kids, small kids, big kids, medium kids. So let's say you're in a gym class and you're asking them all to run. Maybe you're running the mile or whatever. eventually you'll get to a point where some of the students may start to lag behind, leaving the stronger students, maybe the athletes, to sort of pull up front. And that's sort of the idea for dispersion forces, right? You can have a molecule that is moving at super fast speeds, and because of the way this is happening, it causes a dipole essentially to be formed. So instead of having something like a nonpolar atom, like a hydrocarbon, let's say, shaped like this, under dispersion forces, you're going to have something where it has a small dipole. And that's simply because of how fast these atoms, these molecules are moving, and that can cause some attractive forces as well between molecules. So in the end, you might want to talk a little bit about strength of intermolecular forces. Remember, they are not nearly as strong as ionic covalent bonds or anything like that. When you think about it, if you want to relate this to sort of your biology class, and you think about DNA again, we don't really want intermolecular forces to be as strong as covalent or ionic forces, right? Why would we want the DNA backbone, right, the nucleotides, the sugar phosphate backbone, to be as strong as a hydrogen bonds between the nucleotide bases? You know, you really wouldn't want that, because that would require a lot more energy to break apart for transcription, translation, replication. We need to have something that's strong at times, but also weak when it needs to be opened. And that's what we can really get with these intermolecular forces, right? They have a certain temporary aspect to them. As for covalent and ionic bonds, take a lot of time and a lot of energy and heat to break apart. So in general, the strongest intermolecular force would be a hydrogen bond. It's something about that electronegativity and that hydrogen, the delta negative and that delta positive, that that really gives you a strong bond. That's not to say that the other intermolecular forces are just, no good. They all have their own ups and downs. And the least strong intermolecular force is the dispersion force. And all molecules, even all atoms, exhibit dispersion forces, right? Because in reality, they're not just sitting there. Anything that has any type of speed to it has some dispersion forces. They're just not as strong. So even something like a chain of hydrocarbons, which you have probably been told are nonpolar, right? There's not that much difference in electronegativity. When they're moving at fast speeds, there is some dispersion force to them. And that wraps up our talk about intermolecular forces. I hope this was helpful for you. And hopefully this will help you get a better understanding for your Gen Chem class, your high school class, whatever you're doing. So have a nice day, and I will see you in the next video.